Thursday. So I mean, first we announced that it will be on Wednesday, but in fact it's Thursday, 11 o'clock.
Where is Daniel?
Daniel is not here, and that's why he couldn't make it on Wednesday, because he wouldn't be here on Wednesday as well. But on Thursday he will be here. So, but today it's Georgi Rykov, and he will talk about potentials that are both oscillating and decaying, and eigenvalue asymptotics for such Schroedinger operators.
When was it announced about the shift of the seminar? I think it's still on the timetable. It is still on Wednesday.
No, this is
It-
Thursday.
Thursday.
Yeah, it's fine.
If you look on the board, it's Thursday, yeah.
Okay.
Shall I start?
Yeah, absolutely.
You are on there, by the way.
Thank you very much for the invitation and for the presentation. So, just to say a couple of words. It's a very simple talk, and actually I was motivated when I was looking at some waveguides with perturbed periodic twisting, and there I've taken as an effective Hamiltonian the one-dimensional Schroedinger operator, which looked like this. It was self-adjoint LPR, and here W is a function which decays regularly. At infinity, and of course you'll ask what's the meaning of this term. This means that there is some finite smoothness, at least finite, and the derivatives decay faster and faster, while eta is a periodic function. Okay, non-constant periodic function. So when we have the product, this guy cannot decay in a regular way, because the derivatives, well, we'll have the derivative on eta, and in the general case, this function does not, the derivatives of this function do not decay faster than the function itself. So I was interested in the
So
asymptotics.
the regular way means again.
Okay, I'll give them the definition, but once we are speaking about this, when we are in L2RT, I'll give this definition. This will mean that d alpha wx is smaller than, so rho is a positive number, so that we have a decay. Alpha is the mode index, so this is the derivative. So when we take the derivatives, we have faster and faster decay. Here I didn't put any assumptions on the number of the derivatives, so in this case it is infinity, but what I'll have is a finite smoothness. So this is the more or less the definition of regular decay, and when we multiply by a non-constant periodic function, say periodic, it would be more general, we obtain something which does not have a regular decay. So I was interested in the eigenvalue asymptotics of this guy.
So I'm not, it is not C infinity, right?
No, at the moment it is C infinity, then I'll give a precise definition in the talk, exactly of the class of functions I consider. I just want to explain a little bit the motivation. So, because it decays anyway to infinity, the essential spectrum is from 0 to plus infinity, and we could have negative discrete spectrum. So well,
Excuse me for interrupting. Just to understand, so the loss of regularity is due to the precisely a multiplicative form of
exactly.
modulation.
You're completely right, and actually the fact that the function is exactly periodic is not so important. I'll try to explain this. So, but now I must get back, okay, my slides. And now we are going back to the, say, to the, I just wanted to end this motivation part. So I looked at the literature. I was convinced that there are results on the eigenvalue asymptotics for such potentials. I didn't find anything, so I tried to do it myself. I succeeded. In a way, well, I obtained some results, and then I found that similar things also occur in a couple of, or more than a couple of papers by Safarov, Laptev, and Nabokov, but they were related to a somewhat different problem about the location of the absolutely continuous spectrum, but still some estimate of similar type appeared in these articles. So I decided that maybe it is not uninteresting to gather together all these asymptotics and all these estimates, and this is the result of these efforts. So let's go to the definitions now. So first, some very general things which should be here very well known. That this is the Schroedinger operator. So V is the potential. I take it here with sign plus. So it is very well known that this is the kinetic energy operator and this is the potential energy operator multiplied by V. And also, of course, I choose the units so that the Planck constant is 1 and the mass of the particle is 1/2. And then we just some conditions about our potential, the general conditions which are not so important, but still this is a potential which is relatively compact in the sense of the quadratic form. And here there are some very simple sufficient conditions for this. So we could, for example, we could write V as the sum of V which is in LP and the uniform norm of V2 is small. And still further simpler condition, then V is locally in LP with the same P as written here, and V goes to 0 at infinity. So we could have some local singularities, which however are summed with the P power, and in infinity it goes to 0. These are simple, sufficient conditions. And so it is important that we have these conditions of relative compactness. And in this case, we have that the essential spectrum, of course, corresponds with 0 to infinity. This is one version of Hermann-Weyl theorem of invariance of the essential spectrum under relatively compact perturbations. So we have this thing that the essential spectrum is from 0 to infinity. And the trivial remark, which however is important, that of course if the potential is positive, we have no discrete spectrum because the operator is positive. The discrete spectrum would be only negative and the only accumulation point is 0. So we have the situation like this, essential spectrum from 0 to infinity, and maybe some discrete spectrum which is negative, which would be finite or infinite. And more or less this is the topic of the talk. When the spectrum is infinite, when it is finite, and if it is infinite, what is the asymptotics of the eigenvalues which accumulates to 0. So here we introduce the counting function. E is the energy, it could be negative or 0. And this is just the number of the eigenvalues of this operator, smaller than E, and counted with the multiplicities. So I am lazy in my notation, I just indicate the potential, not the whole operator HV. So this V is the potential of the corresponding Schrodinger operator. So, and what is known, a lot is known actually. This operator has been an object, well, the discrete spectrum of this operator has been an object of very intensive studies in the 1960s, even maybe earlier. So still here I would like to recall some results. Of course, this is the famous estimate of the number of the negative eigenvalues. It is important that here we assume that D is greater or equal than 3. And then we have the following estimate. So the number of the negative eigenvalue is estimated by this integral. So here we have the negative part of the potential, and actually this is some bridge between the quantum mechanics. This is a quantum mechanical quantity here, and this is a quantity from the classical mechanics. What is written here is the volume or the measure of that part of the phase space where the symbol of the operator is negative. So okay, and here we have just this will be used also in the sequel. This is the volume of the unit ball. So this is a very well-known celebrated result, and also some versions of these results are also true in the case d equal to 1 and 2. Attention, these are exactly the dimensions which are smaller or equal than the order of the operator 2, and then the estimates are more complicated. If d is equal to 1, I decided to write an explicit here estimate, so we assume that the negative part is in L1. With this weight, then we have such an estimate, something which is very well known, and it is unimportant in this talk, but this one here is sharp. This means that even if the negative part of V is small but not 0, we have at least one eigenvalue. And in the case d equal to 2, I was lazy enough not to write explicit estimates, but also they exist. Actually, why I was lazy here, just because I will not use all these estimates. Okay, maybe I'll use the estimate 1, but not all the estimates. And actually, I'll use some extremely simple fact that if we have that the negative part admits such an estimate, okay, it's bounded and it assumes such an estimate, and rho, the decay rate, is bigger than 2, then we have finitely many eigenvalues. So actually this is a very simple fact, and it follows from the estimates which I showed. So the problem is whether the decay rate, the exponent rho bigger than 2, whether this is a sharp fact. And here we have the following theorem. I don't claim that the assumptions are the sharp ones, nothing like this, but still this is the theorem which more or less could be found in the fourth volume, I think, of monography by Lichtenstein. So we have the following assumptions. So this is the conversation about regular decay. So we have that V decays. Here we have rho, which is between 0 and 2. Then we have that the gradient decays faster. Here we have minus rho minus 1. This is exactly regular decay, but not more than 1, well, derivative of order 1. Here this means that essentially at infinity the potential is negative, and as a decay rate it is equivalent to x to the power minus rho. And then we have the following asymptotic result. We have infinitely many eigenvalues. We have the Tronic function, so we count the eigenvalues up to e, and e is strictly negative, and then we let that e to 0, and we have the following quasi-classical asymptotic formula. So again, this is expressed in the terms of the phase space volume, where the symbol is smaller than e, I think. Okay, and here I just wrote the order of the asymptotic. So this is the order of the asymptotic. So it is exactly negative. It should be negative exactly under this condition that rho is smaller than 2. So again, this is a very well-known result, but here we have a condition which is important, that we have some kind of regular decay. So again, is it so important that here we have minus 1? Maybe we could have minus 1/2 or something like this. Yes, in many cases this is possible to do, but still here we should have minus some positive number, and this exactly means regular decay, that the derivatives decay faster than the function itself. If we speak a little bit about maybe two fancy things, this could be interpreted in a way in terms of pseudo-differential operators. So if we have commutators of symbols of pseudo-differential operators, in the commutator we exactly obtain the derivatives of the symbols. If we expect semi-classical behavior, then the commutators, which is something typically quantum, should be negligible than the products of the operators. So from this point of view, it is expected, well, that the derivatives should decay faster than the potential itself. And then we have this result.
Sorry, do I understand from what you said? Do I understand correctly that there are some commutators hidden somewhere when you prove this?
No, I said that maybe these are two fancy things, but still, what is the origin? What is the origin of this condition? In a way, this is one way to see it. That actually the derivatives of the potential would appear if we apply some well, pseudo-differential calculus, and we could have these derivatives. Of course, you could obtain the proof of this theorem, which I don't know, absolutely about thinking about any commutators, and even maybe without knowing what commutator means. Still, this is just, I said that maybe these are two fancy things, but still, this is also some way to see the reason, nothing more. And so, okay, we had rho bigger than 2 and rho smaller than 2, and for some reason I also prefer to give the situation when rho is equal to 2. This is the borderline case. Maybe if I have time to say everything I planned, maybe you'll understand why this is also important for me. So in this case, actually, this is not exactly a semi-classical formula. The order logarithm of phi is okay, but the coefficients are not semi-classical. And here our conditions are a little bit different. So we suppose that V is asymptotically homogeneous of order -2 at infinity. And then we have the following asymptotic. So we have that this quotient has a limit, which is this number here. L, once more, is the limit which we suppose to exist of this function. And here we have such formula. So this is the negative part of this number. 1/4, or here d minus 2 squared over 4, of course, is the Hardy 1/4, the famous Hardy 1/4. And attention, when we have d equal to 2, then this number disappears, it's equal to 0. And lambda q is something which I explain in words without writing the expression. These are the eigenvalues of the Beltrami Laplace operator on the unit sphere. The explicit formulae are quite well known, and the multiplicities also are quite well known. I don't want to write this here. The important thing that always the first eigenvalue is of course 0, and it is simple, and of course it corresponds to the constant eigenfunction. So when q is bigger, this is more and more positive, so it has less and less chances to well, that its negative part is strictly positive. And but still, if this number is 0, still we don't say that that there are finitely many eigenvalues. This means just that the number of the eigenvalues is O small of logarithm of phi. But if this quantity is strictly positive, then we have finitely many eigenvalues. I haven't cited almost here the authors of the theorems, but I know this theorem from an ancient article by Werner Kirsch and Barry Simon from 1988. It's true that they didn't write for any dimension. They wrote it for dimension 1 and 3, I believe, or 1, 2, 3. But anyway, they mentioned that actually in the same way you could write the asymptotics for any dimension. So this is enough as known results. But now we come to my results. So this is the problem. What happens if we have V potential, which is the product eta multiplied by W. This is exactly this thing in the case, any dimension. And now let's start to look at the precise definition, what is exactly oscillating and what is exactly regular decay. Okay, for one reason or another, I cannot do it with probably optimal smoothness, but still it is some fine smoothness. And so here I have this definition of this class. This is exactly the condition I wrote here, but I don't suppose that it is for that the functions are C infinity. I suppose that there is some finite smoothness. So even it is possible that they are just continuous functions. This is also a useless notation. So if M is infinity, I think that sometimes this is called the Hermann class of order minus rho. And also here you could have some positive number different from 1, but for the moment, for me, this is okay. So this means regular decay. This is similar to what I wrote here. And then what is oscillating? And here I would like to speak a little bit more. So I could say that this is some nice function, I mean smooth function, periodic function, but I would like to underline that periodicity is not so important. And the result are some notations which could be a little bit ugly. Still, this is a function which is written like this. So here J is the set which is from 0 to L. L could be finite or infinite. So in any case, I suppose that this series is absolutely convergent. So in particular, this is a continuous function. And okay, this is important to say our conditions about CL. I don't know how I should call them, but maybe they could be called wave vectors. So they are in RD. So the first is always 0, and the other wave vectors, they are separated from 0. Okay, the infimum of their length is strictly positive and is denoted by R. So this is of course sure, this is true when we have periodic functions, and the mean value then is eta 0, which corresponds to the wave vector x0, and eta 0 is could vanish or could be different from 0. The other coefficients are supposed to be different from 0, just not to explain that, well, to introduce the set of coefficients which is different from 0. So this is almost periodic function, which has
So you don't mind two frequencies being very close to each other. You just don't want them to be close to each other.
Exactly. So they could have some other accumulation points different from 0, and then exactly that. This is what I want to underline. That's why I decided not to speak about periodic functions. So this is okay. And the other thing, okay, just continue here a little bit. Just so I introduced the usual standard unitary Fourier transform on the Schwarz class, and then of course by duality, whenever I like, I extend it to the dual Schwarz class. And then our condition, well, about the wave vectors is that
Computer.
Switch to. Maybe I could switch to my computer.
Did you press it?
No, I don't think so.
Hi, this is Leonid Parnovsky. We are having something is wrong with the computer. It's stopped showing the projection. Okay, thank you very much. Thank you very much.
Check.
Oh, you must have stepped over.
Yeah, okay, this is enough.
Вот и сам себе коллектор. Naive common sense.
Look from graph that is graph the table from the computer.
Everything is recorded. Even now.
So we should be careful about what we say.
Well,
They said it's not recorded.
It is.
It's not
No,
all
yeah,
from-
so
It
this
is.
okay, so we are waiting for some.
They are sending somebody, yes.
So maybe workshop. Oh, here it will be. There is another one. Okay.
А что? Ну, скажи, пожалуйста.
There was a message no signal.
У меня еще будет здесь.
Yes.
Большой последователь.
Look at it again on the whole screen.
Оба органайзера не возражают. Я могу спираться, так сказать, даже.
So, okay, thank you very much. So,
So what happened? What was the problem?
Magic.
Your presence is important.
Yes. Okay, thank you.
So,
Perfecto.
so just to recall the last slide that we have this condition. So this means exactly that the way that the zero is, if present, is isolated point in the support of the distribution of Fourier transform of eta. So, okay, anyway, a leading example, of course, is a periodic function, and again, I recalled our, well, main hero. This is the mean value of the function eta, which is just eta 0. This is the mean value. So, okay, and then we just, let's go to the main theorem. And now we have the theorem, and actually there are several cases. First, we assume that W decays in a regular way, and here we have some 2n. N is an integer number, positive integer number. Eta is a real valued, of course, almost periodic function in the class I described. And then we have, okay, always we assume that rho is between 0 and 2. I'll make a comment at the end. And here we have the smoothness, which is described in a little bit awkward way, but if I have time, maybe I'll explain these numbers which appear here. More or less, we add some smoothness, which is different in the case D1 or 3, 2, or D is bigger or equal to 4. So this is the first theorem, where in the case when rho is between 0 and 2, and also we have the W is equivalent at infinity to minus x to the power minus rho. Again, rho is between 0 and 2. And here we have two cases. Eta 0, only the mean value is positive. Then we have the semi-classical formula, but eta is replaced by eta 0, so W is essentially negative at infinity, and pre-multiplied by a positive number, everything is negative at infinity. So we have this formula, but again, the true potential, eta W, is replaced just by a regular decaying potential. And the asymptotics is the same as before, the order of the asymptotics, although this is not the semi-classical expressions if here we had just eta. And when eta 0 is negative, we just have finitely many negative eigenvalues. Note that in this case, we could have huge part of the phase space where this function is negative, of course, but still when the mean value is negative, actually we have finitely many eigenvalues. So what happens in the case when we have eta 0 equal to 0, the 0 mean value? Actually, this is exactly the weak point of the theorem, and actually this is exactly the potentials which are interesting in the papers by Safonov, Laptev, and Nabokov about the location of the absolute continuous spectrum. So here we have just an estimate, and we show that in a way we could replace W by the square of W, but only in a way. So here the estimates are as if we have the square of W, that means faster decay. So still we have a function which grows when rho is between 0 and 1. When we have the borderline case, rho is equal to 1, so multiplied by 2, this is 2, we have a logarithmic estimate, and then we have finitely many eigenvalues in the case when rho is between 1 and 2, but that is, I don't have any asymptotic formula. And
So you don't even know whether this is precise.
No, I cannot say that actually I have lower bound. Even I don't have lower bound, which is
Slightly worse.
which is slightly worse. No, so from this point of view, I see what is true that this is just okay. And then I would like also to show the case when rho is equal to 2, and in this case. I have something very similar as in the case of regular decay. Again, I suppose that this limit exists, it's just a real number. And again, I have this function CD, but instead of L, which is, okay, I have just the product of eta 0L. So actually, again, okay, this would be the limit of the effective potential. And again, we have the condition that if eta 0L is strictly bigger than this number, then we have finitely many eigenvalues. This is not very good to write 3, but this means that we have finitely many eigenvalues. So the trivial answer to the question why only rho is up to 2 between 0 and 2, of course, if we have that rho is bigger than 2, just for trivial reasons, then anyway this potential eta times W decays fast at infinity, and because of the estimates I already showed, we have finitely many eigenvalues. So this is just a trivial corollary from the other facts we discussed before. But now I would like to, because I have some time, I would like to try to explain the proof, which I think is.
Sorry, may I also ask something? So in both the result without periodic and in your result when rho equals 2, when limits are not uniform, so we have different directional limits, is anything known?
I don't know. Probably it is possible to obtain something. Actually, I'm cheating. I'm lying here a little bit that I don't know. There is a really recent article by Andrew Hassel and co-authors. Andrew Hassel works in Canberra, if I'm not mistaken, in the Australian National University or something like this. So it is.
But this is Hassel who has done some work on spectral entropy, yes?
No.
Okay.
Probably we should just
Okay.
open the computer and look at Martinez. For the moment, I'm not prepared to answer this question. But anyway, this is resulting exactly in this direction when you don't have a limit which is a number, but you have a function which is homogeneous of order 0. There are some results, but okay, they use some pseudo-differential techniques. But at this moment, I'm not well prepared to discuss this because anyway, the results become quite complicated. You have a zoo of assumptions that if this happens and if that happens. So this is what I just prefer to present here, because in a way this is easy to compare with the case of regular decay. So we just have a regular potential, which is the product of the mean value and W, and it is easier to compare. So there are results by Hessel, and there are some co-authors, which I don't remember the co-author. So, and now I would like just to say a little bit about the proofs. So there are a lot here of notations. We could skip them because they're not so essential. The only thing is I would like to introduce the notations, the counting functions for compact operators. These are notations which come from the works of Biermann. So T is a compact operator, self-adjoint compact operator in a Hilbert space. So this is n plus or minus of S in T is just the number of the eigenvalues of T which are bigger than S in the case of in this plus, or smaller than minus S in the case of sign minus. So the operator is compact, S is strictly positive, so these are finite numbers. So what is not important here is, just in this talk, these are the so-called Weyl inequalities, which help to separate the principal part and the part which is negligible in the operator, and at the same time they immediately make us lose any hope for sharp estimate of the remainder. So this is not important. And also, very briefly, I introduce the number of the singular values of the compact operator T, which is not obliged to be self-adjoint. And here, this is just the number of the singular values of T, which are bigger than S. S is a positive number. There is an analog of the Weyl inequalities in this case, which are the so-called Chi-Fan inequalities. Okay, so this is not so important. And also we have the Biermann-Schroedinger principle, which probably is known to everybody. Still, I wrote it here in an abstract form in order to underline that it is not only for the Schroedinger operator, it is for quite general abstract pair of operators T and S. So here we have the Biermann-Schroedinger principle. So the numbers of the eigenvalues which are smaller than minus lambda for this operator, T is positive and S is self-adjoint and relatively compact in the sense of the quadratic form. So this guy is equal to this guy, and here we have already our counting function n plus and minus, and here we have a compact operator due to the conditions we have. And immediately we write the Biermann-Schroedinger principle for our operator. I recall that this is the counting function, the eigenvalues up to E negative, for the Schroedinger operator with this potential. And then we apply the Biermann-Schroedinger principle, and immediately the unitarily of the Fourier transform F I introduced. So just to say, of course, T is minus Laplace, minus S is the potential. In our case, in the beginning, T is equal to 1. And then under the Fourier transform, this operator passes to this multiplier. So this is here the multiplier which appears here and here. These are the two Fourier transform, and this is the potential. So this is just the Biermann-Schroedinger operator which will estimate. So this is the Sasha, is it okay? And then actually the important thing that in the momentum representation, the important point is psi equal to 0, because if we look, just a second, if we look at this multiplier, actually away from 0, this is just a bounded multiplier, even if is equal to 0. So the important point is psi equal to 0. So we separate the dangerous part and the rest, and this is exactly here. So this is here is the ball centered at 0 of radius delta, and R is not just some R which is some number. R is the infimum of the non-zero wave vectors. This notation appears, so this is like this. And even I wrote it here, so this means that these are the non-zero wave vectors. And so I recall that this is the Birner-Schroedinger operator. We just write it like this. Here we single out the mean value, then we have this guy. So here we have the two multipliers with the same number, x1, x1, x2, x2. And here we have the two multipliers with different numbers. And we have the real part of this thing. And finally, of course, this is bad for you, but for me it is convenient to introduce a new notation. This is some weight function. So, and here we have nu. When nu is 0, this is something which is equivalent to W. When nu is positive, a little bit positive, this guy decays faster than W. When nu is smaller, is negative, this decays less rapidly than W, and of course if mu is -1, this is just a constant. So this is just some weight. And then here we have some very, very long estimates, but still it is not so complicated to understand what we have. So here, roughly speaking, not roughly speaking, but we have the Birner-Schroedinger operator. Okay, after the Fourier transform. So we have the effective potential, and here we have something which decays faster than W itself. Here we have this guy, and here we have chi1, chi1. Here we have this guy, and here we have chi2, chi2. This is a relatively simple function. So here is the initial Birner-Schroedinger operator which we have to estimate. So we estimate it from above and from below. And here we have more or less the same terms. Here instead of minus, here we have plus. Here this is exactly the same term. And here instead of minus, we have plus. So what we want to make in this step, we just want to prove that these two guys, well, their counting functions, they remain bounded when E goes to 0. This is the whole thing. And although this is a very long expression, this is quite easy to see. So this is the difficult guy. So, okay, let me see whether I have time to... So, and now actually this is before we had estimate of operators, and now we have estimates of counting functions. So again, this already, again, I applied the Birner-Schroedinger principle in the other direction. So we have a potential like this, and it is already something which is quite similar to our effective potential. S could be sent to 0, and this is a guy which decays faster than W. Here we have two guys. Here we have two guys, and we'll show that actually these two guys, they remain bounded when E goes to 0. And now actually this is evident because already I don't have E, I have 0. So this is the difficult guy. This is the difficult guy. This could seem very ugly as a notation, but after all, this is evident that this is a compact operator. So we have just function which decays into infinity, Fourier transform, another function which decays to infinity. Everything is bounded, and of course this is a compact operator, and nothing to say this is a bounded quantity. So this is the operator which we have to estimate. And so here we have again chi1, and chi1 is the characteristic function near the origin of the ball near the origin. And so just maybe it's better to skip this. But in the case, well, the case which is not so successful, that is when eta 0 is equal to 0, we have an estimate. I skipped here the comments of this estimate, but actually it is close to the article by Oleg Safronov, which is written here. And actually, about this, without this estimate, if I just use my estimate, I have even an absolute worse estimate, the upper bound. So this is exactly to make the estimate by absolute better. So this is an estimate which in a way follows the idea of the work by Safronov. Okay, and then, so this is the important thing in the rest of the proof. So we just have to prove that this guy remains bounded for any s. So here this depends on s, but for any s it remains bounded when e goes to 0. And okay, so if we have this, more or less, this is the end of the proof, as I try to explain. And now here we need something which probably is known to most of you. I don't know. So if we have infinite smoothness of W, this is a very well-known fact. If we have the complete Hermander class with C infinity, so this is true for any alpha, we know a lot about the Fourier transform. We know that it is C infinity away from the origin. We know that it decays faster than any power, and it has some singularity at the origin. So these are things which are known, but I have learned a little bit more. So I'll skip the proof in this case, but still, if I have this smoothness which is indicated here, then the Fourier transform, you don't see the head, but it is there. The Fourier transform is in the class CAM away from the 0. So here I have just erased a ball of radius epsilon, and also these guys actually are bounded. Bounded actually, even they decay into infinity, but for the moment this is not important. And here I have just the finite smoothness. So this n which appears here is just the number which guarantees this property of the Fourier transform. Okay, just it is possible also to assume axiomatically these properties of the Fourier transform, but I prefer to just explain that we have some regular decay and things like this, so I prefer to give the assumptions in terms of W, not to give axiomatic assumptions of the Fourier transform. So, and now I skip the proof. It is more or less standard proof on Fourier analysis. I'll skip the proof of this lemma, and then I'll try to explain the proof of our proposition. Of course, you already don't remember the proposition, but the idea is to prove that this compact operator, its counting functions remain bounded as e goes to 0. And here, this is the important thing, that because we have chi1, I think that it is quite 1 chi1, actually we can multiply for free the Fourier transform of W by a function of compact support. This is easy to see when we look at the integral kernel of this guy. That is for free. We could replace this guy by the convolution of itself with the Fourier transform of theta. I don't care about direct and inverse Fourier transform here because the function is even and it is just the same. So the function is equal to 1 on the ball of radius delta, and vanishes a little bit on the complement of a slightly bigger ball of radius kappa. I think it should be somewhere here, is the kappa. Again, r is the infinite of the length of the non-zero eigenvalues. And then we have something like this. Actually, when we have this potential beautiful V, calligraphic V, actually we show that Schrodinger operator with such potential can create more than finitely many negative eigenvalues. So this is the whole idea here. So here we just make this estimate, and here we obtain the Schrodinger operator with such potential. So V is this convolution, and more or less this is all. Actually, further we apply our lemma about the Fourier transforms, and here, well, this is the most technical part, and I understand it's a little bit difficult to follow, but still I have a little bit of time. So maybe it's possible here to. So this is the Fourier transform of our potential. So here we have the, say, Fourier coefficients, and the important thing that here we have a shift by XL, and XL is, they are non-zero wave vectors. So because of this shift, actually when we look at the support of our function theta, actually we have smoothness of the individual guys who are here. And also we have eta L, and it is supposed that eta L converges absolutely, so we could sum up everything. And exactly here we could say that it's not important that, well, it's not dangerous when there are some other accumulation points of XCL. The important thing is that they are away from zero. Then with this condition, when we have this condition, we find that this function is continuous and bounded. Actually, just this part is continuous and bounded, and we multiplied by a function C infinity with complex support. And then more or less we are done, because we have that this function, for example, is in any LP. And okay, just this is the essential bound on the LP norm. So this is just the convergence series. So this is the supremum of the Fourier transform, which by the lemma is finite. And finally, here we have the LP norm of theta, which of course is finite because this is a C0 infinity function. So just to say a little bit, I mentioned several times the articles by Safronov and Laptev and Nabokov, and actually only had I found this when I had my text. He had a similar argument, only in his case this function which is here theta, it's not C0 infinity, it's just the characteristic function of some ball, and this creates some difficulties, of course, because it's not smooth. And a little bit further, I'll just see that sometimes it is good to have a function which is smooth. So in this case, I have this estimate, and this is important. And now, just here I explain a little bit the, no, not yet. So if D is bigger than or equal to 4, I could apply the Hausdorff inequality, and then to apply the Zwickel-Lip-Rosenbaum estimate. So that's why it is important to have D greater or equal than 4, so that D over 2 is bigger or equal than 2. And then so here I have the some LP estimate of my of the Fourier transform of my potential. So this is okay, but I don't have the Hausdorff-Young inequality when D is 1 to 3. So from this case I use exactly the smoothness, and so just briefly using the smoothness in this case. So I use also the smoothness of theta. Then my potential decays faster than x squared, and in dimension 1 and 3 this is sufficient to conclude that there are finitely many eigenvalues, because we're in 2 and 3. In D equal to 2, this is not exactly the case, and because I'm lazy, I just suppose that we have more smoothness, then I can write this thing, so V decays not faster than x to the minus 4, and of course in this case again we have finitely many eigenvalues. This is of course vulgar, we could assume less smoothness, but still this is well, something reasonable. For example, in the case of the assumptions of Fourier, he just supposed that the function is identically zero in a vicinity of the origin. Still, it is better to have some, excessive smoothness. Okay, then identical 0. And so the thing which I already mentioned, we had another guy which is related to the x2 function, but this is something which is simple. I try to explain this. So here we have a function which decays into infinity, another function which decays. This is a function of x, this is a function of psi. And this is very simple lemma that if we have two functions which decay to infinity, it's not very good. Here I should have written psi and here x. It's not good to write like this, but anyway, then this operator is a compact operator. Again, no pseudo-differential operators, but one could say that it is known that if the symbol of pseudo-differential operator decays, the operator is compact. Here, one doesn't use pseudo-differential operators. So, just to say that this is all, actually, I just want to go to our big estimate, which was like this. So, once more, in these two propositions, technical proposition, we proved that this is bounded, which was the more difficult part, and then this is bounded. And of course, this and this are bounded. And then we are left with this guy, which is the main term, and this guy. And roughly speaking, this is exactly our effective potential. Here we have S, which could be sent to 0, and here we have guys which decay faster than W at infinity. So, just applying some of the results on which are known on regularly decaying W, we could obtain the main results of the theorem. And that is everything I wanted to say. Thank you very much for your attention.
Thank you. So you mentioned some results by Safronov, Laptev, and Nabokov, yes?
Yeah.
So what exactly have they said something about positive spectrum, for example?
Oh, actually, there the whole thing is about the positive spectrum, but it is some unexpected relation between the positive spectrum and the eigenvalues. And these are put by memory, but more or less the result is like this. So now we have this operator, so this is HV. And then we have lambda G. I have another lambda, forget about this. These are the negative eigenvalues of this and of that operator. So we have minus V and V. And now assume that for the moment I'm going to say that the number is finite or infinite. Assume that we have this thing. So this means that they could accumulate, we could have infinitely many eigenvalues, but this series converges if it is infinite. Then we have, if I'm not mistaken, that the absolute continuous spectrum of HV is supported on 0 infinity. So this is a result like this. If you lie here at V and minus V, okay, just and we look at these two operators, we see that in a way, if we have the function eta, this should mean, well, results like this should be related exactly to the case when the mean value of this function is 0. This is a little bit vague, but after all, we have something of this type. So, and when you write this infinite sum, you arrive to some estimate exactly of the negative eigenvalues. You can write this exactly as an integrals of the counting function, and then you have to estimate the counting function. The estimates are different, but still this could work, and this is something which was obtained, and exactly this thing was in an article by Sokolov. That's why I always started with his name, because he's the author of this article in CMP in 2005. It appeared at some moment, but before that there were several articles by other authors, and they concerned the one-dimensional case, and here I could mention authors like Domanic, Melipexidant, and some other people. So this is the case where we have the one-dimensional case. So they preceded these articles, and they're quite different, of course, in flavor and in method, because they.
But they also studied absolutely continuous.
Yes, well, results of this type.
So what about eigenvalues? Embedded eigenvalues?
Okay, this I don't know, but actually I had a very brief discussion with David here during the semester, and he told me that exactly when I told him very briefly of my results, he immediately asked, what about embedded eigenvalues? I said, no, this I don't know. And I tried to explain to him that actually there are many variational aspects of my proofs and things like this, and it's, for me, it's unthinkable to approach embedded eigenvalue. And he said, okay, we also started with discrete eigenvalues, but then it turned that it is possible to go to embedded eigenvalues. This I don't know the results, but you see, in the one-dimensional case, it's many things are much easier. So, well, in there, and even he had some PhD students with him, and he said that this is his thesis, more or less. So I don't know the details. And these articles, they are quite old. They're much before than the articles by Safronov, and this is CMP 2005, and there's another article by Laptek, Nabokov, and Safronov. The same journal, the same year, but not the same volume. Okay. This is all. What can I say without further looking in what's in it?
Okay, so it's not even, as far as you know, it's not even known whether you could have dense eigenvalues.
No, this I don't know. This I don't know. But actually, this is the result. Probably something like this is known, but I don't want to comment things which I'm not sure of.
Valera?
Again, the initial assumption was product form, so periodic times decaying function. Can this be generalized in some way? I suppose, like, if I have sum of the two, eta 1 W1 plus eta 2 W2. Will that work?
Oh, actually, there is an enormous zoo of possible generalizations and extensions.
Right.
I haven't thought exactly of what you're suggesting, but I thought about something random. So it is some random process or multidimensional process with some condition of the type which I mentioned here. So in many cases it's possible to define the distributional Fourier transform of a random process, and under some condition of this type it is possible to extend the results. And the other thing which I would like to see, if it is so important to have this condition that the wave vectors do not accumulate to zero. I try to overcome this assuming that eta L are summable, not just summable, but summable with some growing weight. For the moment it did not work. So
Actually, we talk about zoo. I mean, another possible generalization would be periodic plus something of your type.
oh, but periodic
And
is
then see what happens in the gaps. I mean, what happens in the gaps of.
this of course. I already thought, but okay.
Couldn't you do like this, like a priori you have a function of two independent variables x and y,
Mm-hmm.
and function is periodic in y and decaying in x, right? And then you just replace y by x.
I haven't thought about this, but it is possible that it will work. I don't know.
The kind of two-scale function which is periodic and decaying simultaneously.
Actually, you see, as far as I remember, but I have to open the articles, Laptev, Nabokov, and Safronov had some functions of this type, but I should look at it again.
Further questions? Okay, let us think maybe again.